Alright, ladies and gentlemen, if you're watching this, you should have chapter 10.1 notes in front of you, and you should have already picked up homework set 10-1. Chapter 10 is all about how atoms or molecules move in relation to each other, and what happens when we heat them up, and what happens when we're looking at gases versus solids, and the changes between solid, liquid, and gas. So stay with me and make sure you pause if you need to jot down any notes. So we'll start with the whole basis of what we know about how molecules move. Everything that we know is based off something called the Kinetic Molecular Theory. The Kinetic Molecular Theory is a model that we use to explain the properties of solids, liquids, and gases in terms of the energy of the particles and the forces that act between them. This is based on the idea that particles of matter are constantly in motion. Now, it's very important to realize that this idea can never be proven absolutely true because we've never reached the point that they're not in motion. We've never gotten to that point of absolute zero where we know that it can exist without motion. The kinetic molecular theory of gases is based on 5 different postulates. Now I'm going to go through the 5. Make sure you jot these down in your notes. You see them indented right there. Gases consist of large numbers of tiny particles that are very far apart relative to their size. Now, they're very far apart because they have very high motion. Most of the volume occupied by a gas is empty space. Collisions between gas particles and between particles in the container wall are elastic collisions. That means that there is no net loss of kinetic energy, meaning as I bounce around the little box here, let me pull this up here. As I bounce my little things around the box here, say this is an enclosed case and this is a gas particle moving. Elastic means I don't lose any energy because they're hitting the walls. All right. Another thing you need to know about gas particles is they are continually in rapid random motion. Therefore, they always have kinetic energy because they're always moving. Now, there's no potential energy to it because they're constantly moving. Potential energy would exist in something more like a solid, but even we know that those are vibrating. There are no forces of attraction between gas particles, therefore those particles won't stick together and become liquid. The 5th postulate is the temperature of the gas depends on the average kinetic energy of the particles of the gas. So this one's huge, guys. The temperature of a gas depends on the average kinetic energy. As I increase the temperature, I'm increasing kinetic energy. Does that make sense? As temperature goes up, kinetic energy goes up. Now, something very important to understand here is kinetic energy, which you may have learned this last year. The formula that we use to find that is 1/2 the mass of the gas, particles, whatever, times the velocity. Let's see if I can move this guy. Velocity squared. What's important to realize here is that the velocity tends to count more than the mass, okay? So this means that the kinetic energy is measured based more on the velocity of particles than it is off of the mass. So think about it, guys. Whether I have a tiny little sports car or a huge dually pickup truck, if they're flying down the road, if that little tiny sports car is going faster than the big giant truck, the tiny sports car is going to have more energy, therefore a bigger impact if there was an accident. You do need to write down this equation in your notes just to have it. Okay? Okay, all gases at the same temperature have the same kinetic energy. So say I had a sample of oxygen and a sample of hydrogen gas, if they're at the same temperature, those particles have the exact same energy. Okay? Now, if they're at the same temperature, the lighter gas particles have higher speeds. Okay? If they're at the same temperature, the lighter gas particles have higher speeds. So which would be lighter? Oxygen with a mass of 32 grams per mole, or hydrogen with a mass of 2 grams per mole? Well, the faster one, of course, would be the hydrogen, as it's not weighed down as much by gravity. But they both have the same kinetic energy. So right here we're going to talk a little more about the properties specifically of gases. What do all gases have in common? Alright, so here are the properties of all gases. They can expand to fill any container in which they're enclosed. Remember, they'll fill any container. And they move rapidly in all directions without attraction between the molecules. Now, remember this concept later on. Fluidity. Liquids and gases are both fluids because they both flow. Obviously, I could pour a liquid out and it would flow over whatever surface I put it on. But so can gases. Depending on how heavy the gas is, how dense it is, a gas can flow over the floor just like any other liquid would. Think about carbon monoxide. It's quite heavy. It can flow along the ground. And since the attractive forces are insignificant, meaning they don't stick together, the particles glide easily past one another. All gases have a very low density. The density of the gas is about 1/1000 of the density of the liquid or solid state. So when you're in the gas state, the gas is much more likely to sit on top of the liquid or the solid, which you could pretty much assume anyway. Gases generally rise. This is because the particles are so much farther apart. Remember, density is equal to mass over volume, okay? So our mass doesn't change of our sample, but the volume goes way up. And whenever that happens, your density itself goes way down, okay? Compressibility. How much can I squeeze something? During compression, the gas particles, which are generally far apart, they get squished closer into each other. So say here's my container. I can fit gas particles in here up into a certain point where no more will fit. But we can continue to crowd them in there, and they're still going to move, and they'll make space for each other. That's why they are compressible. Gases also diffuse, meaning they spread out and mix with each other, even without being stirred. Think about our atmosphere. Our atmosphere is made up of all sorts of gases. You've got nitrogen and oxygen and CO2 and some sulfate stuff, and there's hydrogen and helium. They mix in together without any specifics to how it works. When they mix together, this is called diffusion. Also, think of this like when you walk into the movie theater, what's the first thing you smell? Well, that would be popcorn, right? Popcorn? That's because the smell of the popcorn diffuses from the popcorn maker all the way throughout the building, so you can constantly smell it. Alright, let's talk about deviation of real gases from ideal behavior. Now, an ideal gas is something we're going to talk about next chapter more in depth, but it's a hypothetical gas that perfectly fits all the assumptions of the kinetic molecular theory, meaning it is always has elastic collision, the particles are always far apart and they're always moving, there's no attraction, and the temperature depends directly on the average kinetic energy. Thing is, real gases don't always fit all of those assumptions, okay? During most situations, real gases, everything that truly exists on our planet, is a lot like ideal gases, but if we change this parameters and put it at very high pressure and very low temperatures, say out in outer space, gases deviate big time from that of the ideal laws that we're going to learn about next chapter. All right? Let's see. Oh, well, we are finished. You need to go work on homework set 10-1. If you have any questions, let me know. Check the calendar to see if you're doing all questions or only the odd questions. That'll change from honors to standard. Just go and double check. Make sure you stay up on these video lectures, as your test will be coming up soon.